So okay, let us start. Let me first write the matrix. I'm putting this date over here because when students will see this video in the YouTube, they will get to know that it is session 2, because I have to start from the middle of the problem, and therefore they will miss the continuation. It could have been better if we could have I could have written session 1 in the previous session, but I thought that I would be able to finish the problem. It is taking so much time. Okay, now see, that's why I told you in the first class of assignment problem that not always the assignment problems are that simple, that after only applying 3 steps you will get the solution. So I'm writing the matrix which I copied from the previous class. This was the matrix. And the minimum lines which we draw, the minimum number of lines that we draw to cover all the zeros were this. And the minimum uncovered element is 1. Now I'm going to apply step number 5 in the following way. Covered elements. Let me write on, first of all, let me write the covered elements which are only the covered elements and not appearing at the junction points. So these covered elements will remain same. So let me write these covered elements first of all. Okay. Now, since this is the minimum uncovered element, that will be added to the covered element which is appearing at the junction point. So let us make it 3 and this one is 4. And from all the other uncovered elements, this minimum element will be subtracted. So 3 minus 1 gives you 2. 2 minus 1 gives you 1. 2 minus 1 gives you 1. 1 minus 1, that is 0. 4 minus 1, this is 3. And 3 minus 1, this is 2. Now, in this way, we have got a new matrix. After getting this new matrix, our job is to apply. So I'm writing over here, after formation of the matrix, by the rule or by the rules stated in step 5, we again apply step 3. To find optimal assignment. So if you are fortunate enough, you are going to get the solution. Otherwise, you have to continue. Okay. So let me write this point over here. If at this stage the optimum solution is reached, the process will be stopped. Otherwise, we again apply from step 5. And we'll keep on doing this until unless we get the optimum solution. So just like in step 3, just like as I described in step number 3, try to find out the row which contains the minimum element. The single zero. So this is the first row which contains the single zero. So we are going to assign this zero by putting it inside a box. Any other zero appearing in this column or row containing this boxed zero will be striked out. Go to the second row. Second row contains 2 zeros. So we shall, for the time being, we shall avoid it. Go to the third row. Third row now contain a single zero. So we are going to assign this. And this zero is appearing in the column 2, in which there is one another zero which will be striked out. And this boxed zero is appearing in this third row, which contains no other zero. Go to the next row. It is fourth row. Fourth row contains 2 zeros. So we shall avoid it. Now come to the column. First column has already got its assignment. Second column has already got its assignment. Third column has got 2 zeros. So we shall avoid it. Go to the next column, that is column number 4, which has got only one assignment. Assign it. Strike out the remaining zero present in the row. And now at this stage, you see whether you consider the second row or the third column, both way, in both direction, from both perspective, you can say that this contains a single zero. So I can now very well assign it. So we are fortunate enough. After this, we have got that in each case, in each row and in each column, we have got one and only one assignment. So now we see that the resultant matrix now contains one and only one assignment. And the Hungarian algorithm is now stopped. The Hungarian algorithm is now stopped. The Hungarian algorithm is now stopped. And therefore, I'm going to write the assignments or you can say the assignment from the given matrix as follows. Okay, so you see the first person has been assigned to the first job. That means we have got this assignment. The second person has been assigned to the second job, a third job. So we have got this assignment. Third person has been assigned to second job. So this one, and fourth person has been assigned to fourth job. That means this. And now you look at the original matrix, the value or cost from the original matrix. So once we assign person 1 to job 1, the let me see the problem. From the original matrix which was given in the problem, the cost was $1. So let us write it out. Just check what is written in your copy, $1. For the second, it was $10. For the third, it was $5. And the fourth, it was $5. So $21 is the answer. $21 is the optimum answer. This is the optimum or minimum cost. Optimum or minimum cost. So if you have any doubt regarding this particular methodology, you can unmute yourself and you can ask me. If you have not understood any particular step, then I'm going to explain it once again. Otherwise, we can go to the next problem. Okay, so I think that you do not have any doubt regarding these steps. So we can consider one another problem at this stage. Okay, so let us consider this problem. This is also I'm also considering a minimization type of matrix. So the problem goes like this. Okay, so the values are 50, 50, 20. Okay, the values are 50, 50, and 20. 70, 40, 20, 30. 70, 40, 20, 30. 90, 30, 50, 10. Sorry, 90, 30, 50. Okay. 90, 30, 50. And lastly, 70, 20, 60, 70. 70, 20, 60, 70. So we have got our matrix, but why have I given you what have I given you now is a special kind of matrix. It's a special kind of matrix which you see, it is a special type of matrix because in this case, here in this at this point and here at this point, dashes have been put. These dashes mean these are the restrictions. Okay, these dashes mean the dashes mean that these are restrictions. These are restrictions. What do you mean by that? This means that the person one, for some reason or other, we don't know what, cannot be assigned to do job number 3. or job or this this machine 3, you can consider this machine cannot be assigned to person 1 because of some reason. This machine 4 cannot be assigned to person 3 because of some reason. And therefore these are the restrictions. With these restrictions with these restrictions at hand, we are going to apply Hungarian method to find the optimal assignment. So I'm not going to do this, repeat the process. I'm going to write a note over here to just save the time. Hungarian method will be applicable. Hungarian method will be applicable to this problem. Hungarian method will be applicable to this problem. Hungarian method will be applicable to this problem as before, but only thing we have to keep in mind is that the dashes will not be considered throughout the problem. I mean, during the entire problem, the dashes will remain as dashes. Throughout the problem, the dashes will remain as dashes. Okay, the rest of the problem will be same. It is just like the problem, it is just like what we have done earlier, but only thing you have to keep in mind that these dashes should not be touched. For example, if you want to apply, the step number 1 to find the matrix. So in step number 1, what we do, we identify the minimum element, and that minimum element is subtracted from the row. So here in this particular matrix, you see the minimum element in this row is 20. So 20 will be subtracted from all the other elements. So in the resultant matrix, you will get 50 minus 20, that is 30. 50 minus 20, that is 30. 20 minus 20, that is 0. And here in this dash, you will put dash. You will not write anything. Okay. So this type of case is sometimes also known as restricted assignment. So it is a restricted assignment problem. And why did I tell you that I told you, I can remember that in the previous session I told you that in the previous session I used the term minimal and not minimum. Why is it so? What is the difference between this minimum and minimal? Okay, so that was not a mistake which I made. I did it intentionally. So minimal and minimum, you have to know the difference between these two terms. I preferred this word because sometimes in the assignment problem, you can get more than one assignments with same optimum value of the cost matrix. Okay, so in this type of scenarios, the solution is not called optimum solution, but it is called optimal solution. So two minimum values are present, two minimum solutions are present. of the same type. Two minimum solutions are present of the same type, and therefore we use the word minimal or maximal. If two minimum solutions of the same types are obtained, we use the word minimal instead of minimum, and maximal instead of maximum. Okay, so this is the difference between the two words, minimal and optimal and optimum. Optimum is always the only one value, only one which you have to consider. Optimal means the solutions are optimum, but more than of this type actually appear. And I do not have any problem. I do not need to, I do not have any problem right now, but I am just telling you a situation where suppose it is a situation, it is not a problem which I'm talking about right now. The situation, suppose the situation is like this. Suppose the situation is like this. So when you are doing the assignment, you are putting it inside a box. You are putting it inside a box. Okay, but in this case, in this type of scenario, you see that in the row 2 and the column row 3, in these two rows, there are 2 zeros, and in these two columns, there are 2 zeros. But step 3 is saying that you can consider only one, you have to consider as row or a column containing only 1 zero. Okay, so what will you do now? Because step number 3 is actually whatever the step number 3 is saying is not happening over here. So shall we stop or shall we continue? And if you want to continue, how to continue at this stage? The process is, the way out is that if this type of scenario happens, then in this case, what you have to do, you choose any of these two elements. Suppose you are considering this row, you have no other alternative but to consider any one of these arbitrarily. So if I can consider one situation like this, where I'm going to strike out these two and assign it, or in the same problem, we can just do the opposite. Let me show you. Since I do not have any book with me, so I am unable to show you the actual problem, but this type of scenario may arise. So in the previous case, we assigned this 0. So you can do just the opposite by assigning that and striking out these two. If this type of scenario happens, then you will find that in both the two cases, what is happening? 1 goes to 1, 1 goes to 1, 4 goes to 4, but 2 can be assigned 2 or 3, and 3 can be assigned 3 and 2. This is happening. If such a scenario happens, you will find that the cost matrix will be designed in such a way that the optimum cost or minimum cost will be same for two different types of assignments. Two different types of assignments I am saying because the person 2 can be assigned either job 2 or job 3. Person 3 can be assigned either job 3 and job 2. Therefore, two different sets of assignments are possible, but the optimum cost in this case will remain as it is. That will not change. And this type of situation is called multiple optimal case. Multiple optimal case. And therefore, we use the word optimal. Therefore, we use the word term optimal and not optimum. Multiple optimal case. Since assignment problem is a special case of linear programming problem, in linear programming problem, this type of situation happens in the simplex method when in the zj minus cj row, we have to select what? The most negative number. But in there are some problems in which you can get zj minus cj row where two minimum elements, two negative numbers, same negative numbers are present. Most negative numbers are same. So in this case, you have to select any one of these two arbitrarily. This type of situation indicate that the problem, the linear programming problem, has a multiple optimal scenario. And the thing which I told you in the last class, that what will happen if instead of getting the cost matrix we have the profit matrix, then what we'll have to do. Suppose a matrix is not a cost matrix, it is a profit matrix. So I'm not writing any matrix over here, I'm just noting the point just on the right hand side. As a question I'm posing it, what if the profit matrix is given? Can we apply Hungarian? Can we apply Hungarian? The answer is no. First, convert the profit matrix into loss matrix, or in other words, convert the maximization problem into minimization problem, and then apply Hungarian. And how to convert? And how to convert this matrix? How to do it? How to convert? In this case, what we do, in the profit matrix, we mark the biggest element and subtract all the other elements of the matrix, including the biggest one. From the biggest one. If you do so, your profit matrix will be reduced to a loss matrix, and then you can apply the Hungarian method to the given problem. One another extra case is there, which I told you in the first class, that about airline assignment problem. So that this is a very practical scenario, this airline assignment problem, where we actually assign airlines to the we actually assign the flights to the routes. There is a beautiful problem over there. I took one class with MBA students in the last semester. I made this video, and they became extremely tired when I actually started doing that. It took me around 1.5 hours, I think, if I can remember. So I'm not going to repeat this in your class. I will share that video with you so that you can have a look at that in your leisure time. If you have any interest in this, in knowing how to apply this assignment problem to a practical scenario. So every other case of this assignment problem has been discussed. The assignment problem chapter is now, I'm going to close now. And in the next class on Friday, I'm going to show you something else, some new topic, okay, that will be discussed in the next class. So with this, I'm going to conclude my today's session. See you on Friday.